Welcome, everybody, to the fourth edition of our online computer vision and artificial intelligence workshop, the hackathon part. I am Jose. I would like to welcome all of you who are watching us at home live and maybe later. Um, as some of you know, I am a PhD student from the Nordling lab, working on deep learning, and now I'm also your lead hacker for these hackathon sessions. So today with me, we also have Rick, Jacob, and Rain. Guys, would you like to say hi to the audience?
Okay. Hi, my name is Rick. I'm an assistant hacker of this hackathon, and I'm also a master student of the Nordling Lab.
Hello, I am Jacob. Also is the assistant hacker in this hackathon, and also is the master student in Nordling Lab and CKU. Thank you.
Hello, I'm Rainwu, your chat master of Hackathon session. As usual, please feel free to write your question and comment in YouTube and Twitch. I will gather them and report to all the hackers.
All right. So thank you guys for your introduction. So this is my second session for today. I had previously done my talk, so you are welcome to go check it out. It's a very interesting talk, a little bit technical, but it's a very interesting talk. Maybe Rain, could you help me to write the link in the chat so that the audience can look at it? Yeah. Please go to say.
Yeah, of course, we'll put it.
Yeah, so please go check it out and like our video if you like what we're doing. It will really help us a lot. um, so today is the fourth edition of this hackathon session. So on the first edition, what we did was to do basically the basic stuff with the OGD. So we basically demonstrated how can we use the OGD to get RGB data, video data, as well as the controlling the two monochromatic cameras on the OGD to get the two black and white. One for the left camera, one for the right camera, and then you can see how it gives you these grayscale values. And then I think we also did a calculation of the disparity map. So because that map is the one that we use in order for us to determine the depth, right, of objects in an image. I think in the first workshop we also looked at how to use multiple OGD cameras uh, to control two OGD cameras simultaneously. And lastly, we did encoding the video in a compressed format, right? For the second and third workshop, we focus more like on our submission to the OpenCV and AI competition for this year, so for year 2021. And well, the first part, the workshop 2, was more focused on like the data collection. So how do we record the hand of the Parkinson's disease patients doing the finger tapping test and extract the trajectories of the fingers. And for the third one, we stepped a little bit away from the OD, but we still in the computer vision field, where we used a 3D CNN. We trained a 3D CNN on the trajectories, on the trajectories and videos of these video snippets of this patient doing the finger tapping test to be able to predict, right, the trajectories from this video data. Then I'm very happy to tell you that for workshop 4 and workshop 5, we're gonna go back to doing more stuff with the OGD, and we're actually gonna do very interesting stuff. Today, what we're gonna do, well, I can show you the outline that we have for today. Today we are doing more practical stuff in the OGD. So we're gonna work in creating pipelines and post processing the results of the pipeline so that we can do two things today. One is face detection, right? So we're gonna use the OGD so that the OGD can collect the data, and then we will have a model. We will put a model in the OGD, and then the model will run inference on the data that the OGD is collecting, and then we will only extract the predictions of that model, right, alongside with the original frame, so that we can plot the results. And you can see how doing this with the OGD is very, very easy. Then for the second code, we will have this social distance code. So what is this code? So basically, let's say we want to build a system that can alert us if two people are close to each other. Let's say, for example, due to the COVID-19, right, you don't want people to be so close to each other. And the way that we determine if they're close or not is based on their faces, right? So we will basically extend this face detection code into 3D using spatial AI to be able to tell you the 3D position of the faces of these two people, right? And then let's say if they're closer than let's say what, a half a meter, then the system will do something, right? And then we care about the face right now because the COVID-19 is it's a droplet virus, so it can only spread through your face, right? It doesn't spread through like just by touching you or something like that. So that's why we decided to build upon the face detection part, and you will see how extending into spatial AI with the OCD pipeline is super, super, super easy for you guys. And it can be done in, I think the second code, which is the largest code, is less than 100 lines. So it's pretty decent length, and a very nice code. So let me start by explaining what is object detection, right? And how have people evolved from the most rudimentary approaches to now what we have uh, today, which is considered state of the art, which is you only look once, YOLO, and single shot multi-bus detector. So let's start by explaining, okay, what is object detection, right? Because when we detect faces, we want to detect an object, and the object in this case is the face. So object detection is a task that analyzes the location and class of an image. And so, for example, let's say that I have an image, right? Uh, so one of the most simple computer vision tasks is that I have an image, or let's say the algorithm is presented with an image, and the algorithm is tasked to tell me, okay, what is in this image, right? Typically now, you will have the item be like a large portion of that image, so that it can tell you that, okay, this image is mostly a scissor, right? Then we have object localization, which tells you like, okay, I know that in this image there is a scissor, and I want to know where is this scissor in this image. So then, excuse me. So then I want the algorithm to tell me the position of this scissor through decoding this bounding box, right? So typically the bounding box is decoded by the y min, x min, and y max, x max that determine the two edges of the bounding box. And that also will tell you like uh, which of the area, right, of the scissor and the aspect ratio of the scissor in that image. And object detection basically refers to doing like combining object localization with classification. But in addition to that, so it will tell you like where is a scissor in an image, and then it will tell you that what probability is it that it's a scissor. In addition, it should be able to detect objects of different classes as well, right? So for example, I could have a scissor and a glass, and it should tell me, it should find both of them and tell me that this is a scissor and this is a pair of glasses. And it should also be able to identify multiple instances of the same object in an image. So in the case that, for example, I have two scissors, it should also be able to determine that there are two scissors in that image. Okay, so let's move on. So what have been the approaches that have led us into what is considered to be state of the art today? So we start with object detection, which is a superclass, and then we started with sliding window approach. Then we realized that this approach is extremely computationally expensive and not worth it for us to use if we want to do it real time. Then we went into the methods based on region proposals. So in here we have the region-based Rcnn, Then we have their improvements, right? There is variants, so fast Rcnn, faster Rcnn, mask Rcnn. And then we have, lastly, the ones that are based on regression, which is what most of the people use today. So one is a unified, you only look once, and single shot multi-bus detector. And we will dig a little bit deeper into all of this in the presentation. So let's discuss what is the sliding window. So in the sliding window, we basically build upon the classification task. So we start by selecting a region, right? And the region right now is okay, let me make this a pointer. The region right now is determined by this box. And then what we do is that we will scan the image with this box, and then we will classify whether is there a car inside this region or not, right? And that's what we will do, for example, for detecting cars in an image. So then you can see that, for example, it will start here, and then when it starts going again, is there a car here or not? Is there a car here or not? And that when it comes to here, it will say that there's a car, right? Because then it passed through the car. Okay, but you can realize that since the size of the object, its position, and its shape are unpredictable. Why are they unpredictable? Well, the size of the object can be different based on whether the object is close or far from the camera, right? The shape of the object is also unpredictable because a car could be like a rectangle if you look at it sideways, or it could be like a square if you look at it like from behind, right? And so, and also the position, because the car could be in any different position, right? Any possible position in the screen, which is determined by the position of the pixels. So it is necessary, if we want to accurately detect objects in the image using this approach, we will need to use windows of different sizes and aspect ratios and have a stride of 1. So what does that mean? So in addition to having this size of window, I will need to have, for example, a larger window, a smaller window, right? And the granularity of these window sizes should also be small, right? Because we don't know what is the optimal size of the objects in my data set. And the same thing for the aspect ratio. And the stride should be 1 because that's the minimum value for the stride. So then you can realize that this method is extremely computationally expensive, and that's why it's not useful for many real-time applications, right? Like, for example, if we were going to do edge AI, right? It would take so long time to do the prediction of where is a car, and the accuracy will also depend on, how granular, how fine this granularity is of the window aspect ratio and window sizes. So then people started thinking about, okay, there must be a better way to detect objects in an image, right? So they came up with this region-based approach. So basically, region proposals is just let me pick up an area of the image that seems interesting, that looks like there could be an object there, right? So then there are different methods to do this. One is selective search, one is objectness, one is category independent object proposal, one is constraint parametric mean cuts, and the other one is multi-scale combinatorial grouping. In this talk, we will mainly focus on the selective search part. That is because that is the algorithm that was used for the original region-based convolutional neural network. So the algorithm basically does this. It will look at the image, right? And then it will look, okay, at the color first, right? So these two cats, I know that this is a cat, and I know that this is a different cat because this cat is black or dark brown, and this cat is is orange, right? So for example, in the region proposal algorithm in selective search, this cat will be a single region, right? And then it will kind of like give me this region here. Okay, let me draw this. This cat will be like all of this, right? All of these things that is black will be a single region, and then the region proposal will be something like this, right? Like you just find where, just draw a box that contains all of these little things in this region, and then the yellow cut will be this region, right? This region here, and then the region proposal for this cut will be a bounding box that contains all of these little pixels that are from this region, right? Okay, but color is not enough, because as you can see here on the next example, this chameleon is green, right? But I know that this chameleon is here, right? This chameleon is green and its environment is also green. But why do I know that this chameleon is here and is not part of the environment? Well, that's because this chameleon has a different texture than the environment. So the first criteria for selecting region is color, and the next criteria is texture. So then the region proposal for this chameleon will probably be something like this, right? And then then this will be the region that will be passed as a region proposal for classification. But then you still need to think about that color and texture are still not enough, not good enough, because let's take, for example, this car, right? A car, this car, let me make it what? Green. This car should have a region proposal that is about this size, right? But and should contain the whole car. But that what happens is that depending on the so the car has these rims. Now these rims are a different color than the red body, right? So that means that they would be classified as a different region, and they're also different texture than the red body. So they would definitely be classified as a different region. So the region for a car will be like this, right? But it wouldn't include, and then it would try to tell me that these wheels are a different thing. That the wheels are a different thing because they have a different color and texture, right? So in this case, because the angle of the car, then the green box encapsulates the wheels as well, but it not necessarily be that all the time. So that tells us that the objects, right, the region proposals, they have a hierarchical structure between each other. So, for example, let's say, so typically our hierarchical structure is represented using a dendrogram, which is this tree that I have here. So basically this tree means that at this level, all the classes are basically, they're just, all the image can be divided into, let's say you have the original image here, and then here means that the image could be divided into two different regions. So for example, like this part, right? At this level of the dendrogram, let's say at a low level of the dendrogram, at a high hierarchy, we will have this kind of partition for the regions. So it just kind of groups everything together, right? It just kind of says that, okay, these regions, it looks the same, so I'm gonna label all of this as green, and then this farmer looks all the same, so I'm gonna label as purple, and the sky looks, more similar than this, so I'm gonna label it also, this color. Then as we move down in the hierarchy, right? Let's say here, then we start to see many more regions, right? That appear, different regions that appear. So for example, here you will start to pick up like this little sheep. You will start to make a differentiation between the head of the farmer and this jacket. You will start to pick up this part here. You will start to pick up this part, start to recognize a different region. And as we go down and down and down, we can see that at the lowest level, it will have so many different regions, and it will even try to split the sky in half. So the point is that we want to find uh, a level in the hierarchy where we have roughly 2,000 regions. It can be either here or here or here, right? And the reason for why 2,000 regions is because they want to have they thought that this was like a nice compromise between finding regions that could contain an item and also something that is not so computationally expensive, right? So in here we have 2,000 regions as opposed to all the possible combinations of sliding windows from before. Okay, so then this is what the region proposal, this is what the Rcnn does. So we have the input image. It will extract regions based on the color and texture, right? So for example, this one, this farmer, and then what it will do, and it will extract roughly 2,000 regions. And then what it will do is that it will push this, get each individual image, and then pass it through the convolutional neural network for classification, right? And then it will tell me, is this a person? Is it a car? Is this a horse? Or so on and so forth. But still, classifying roughly 2,000 region proposals makes the detection not fast enough, especially if you're dealing with a very complex CNN. It makes it that every inference that you run is computationally expensive, and some regions may overlap and leading to many false positives, let's say, right? So then here we have just some improvements of the Rcnn, and we'll just go through this very quickly because this is not the main point of our talk. But in fast Rcnn, basically what we do is that what is done is that the regions are not selected in the original image, but they are selected in a feature map after you have been applying some convolution. So that feature map, as we have seen in workshop 3, convolutions make your feature map smaller, right? And that makes it so that it's more computationally cheap than working on the original image. And for faster Rcnn, basically the network learns how to select regions in that feature map, right? So that's some other parameters that add to the network. And for mask Rcnn, is something that is built up on faster Rcnn, but instead of giving you like a bounding box of where the object is, it just tells you which pixels correspond to which item, right? So it's like a segmentation result. It will give you a mask, right, instead of a bounding box result. Okay, so then we go into You Only Look Once, or YOLO. So YOLO was created in 2016 by Ramon et al. At that time, it was a new object detection method approach that frames the detection as a regression problem to spatially separated bounding boxes and associated class probabilities. So the main advantages of YOLO is that it's unified, and that's why it's called You Only Look Once. Because the region-based CNN, they look twice. They look once to select the regions, and then twice, and then the second time will be to do the classification, right, of these regions. And then because it is unified, it's real time. So basically, what happens is that you saw, like previously, there was a picture, region proposal, classification, and then picture, region proposals, neural network, and then the result. Now it's just the image, right? You pass it through to a CNN, through a convolutional neural network, and then this will give you the detections. So where is the object plus the class probabilities? And then it will give you many different bounding boxes. And then what you do is you do non-max suppression. So you compare the you compare the IOU of these boxes, and then to determine the real prediction. And then you will be able to tell you, okay, here is your person with 0.64 probability. Here's a dog, right? Here's a horse. And that's what YOLO does. So that's why it's called You Only Look Once. So how does YOLO actually do this? Well, excuse me. So YOLO will start by separating the image into an S times S grid. Typically, it is a 7 times 7 grid. And then each grid is responsible for predicting the a bounding box, right, which contains the center of an object. So, for example, if I was going to label this image here, okay, let me make this a different shade of blue. If I was going to label this image here and tell you where is a dog in this image, I would probably do some bounding box like this, right? Okay, so then the center of the bounding box is, let's say, roughly here. So then all of these uh, grid cells are going to tell me that they see a dog around them, but this is the grid cell that will be responsible for telling me that there's a dog. So that's why you see here that we have this this shade of blue, because all of these grid cells would be telling me like, oh, there's likely a dog in here. Then for the bicycle, if I draw a bounding box around the bicycle, it will be something like this, right? With its center probably around here. So this will be the one that is responsible for telling me that there is a bicycle there, but all of this will be trying to give me some prediction for a bicycle. And then for a car, it will be, and that's why you can see that here it is also some different shades of yellow here. And then for a car, it will be like this, right? And then this will be the one responsible, but all of this will be trying to tell me that there's a car there, and apparently also this one's here. And so each of these grid cells is going to tell you a prediction for a bounding box, and that's why you can see here on this top image there's like a lot of bounding boxes. Now, not all of these bounding boxes are correct, right? Not all of these bounding boxes actually contain the object. So that's why you look at the bounding boxes that are the most confident in the algorithm, and then, for example, in this case, it will be this one, right? It will be, and they're determined by, in here they're represented by this thickness of the line. And then for the bicycle, it will be something like this. And then this will be like your final predictions after you do non-max suppression. So then you select these three, right? To be your real output of YOLO. Okay, so now we're going to single shot multi-box detector. So single shot multi-box detector is an algorithm that, similarly to YOLO, is also unified, and it does everything in a single step. But the difference between YOLO and this one is that this one uses a pyramidal feature hierarchy method. So what does this actually mean? So basically, it will have the image, right? And then it will do something to the image that transform it into a smaller feature map. And then what you're going to do is that you're going to try to predict where are the objects for each pixel here on this feature map. So each pixel will be giving you a prediction of a bounding box in this map. So this will give you giving you predictions of where the objects could be, and same thing here, right? Until you get to the lowest level. And why do they do this? Well, the reason for why do they do this is because they believe that objects that are large, objects that are small, are more easily detected at a feature map that has higher resolution. So, for example, this cat will be more easily detected when you have an 8x8 feature map, as opposed, because it's smaller than the dog, right? When the dog is the dog is a bigger object than the cat, so the dog will be easier detected when you have this this bounding box on a smaller resolution feature map. And then so it will get all the predictions here, and then it will I think that well, in the next step we can see it will do non-max suppression on all of these detections, and then it will just give you the output, the final output from based on that. So as we saw before, the pyramidal part is just now lying down. But basically, what you do is that you have an input image, and then you pass it through a network. This in this case, this is VGG16. So what this does is that so you only pass it through the feature extracting part of VGG16. So only through the convolutional layers of VGG16, and then that will transform the image into something that is 38 times 38 times 512. And then with this, then it's much easier to work with. Or this is your highest resolution map that you're going to do the classification, sorry, the detection. And then after this, you're going to add additional convolutional layers to make your make your feature map smaller, as we saw on before, right? Convolution tends to shrink the spatial dimensions of your feature map, and then that's gonna make it smaller and smaller and smaller. And that's as we mentioned before, it is to be able to do detections at different scales, right? And then you will do a non-max suppression on all of these detections to give you the final output. Like it will like this do this kind of like a weighting, right? So here we try to find a comparison of Rcnn and SSD and YOLO. So this is, to be fair, this is a comparison that we saw on the YOLO v2 paper. So these are just different architectures of the YOLO v2, and I think they are being tested this on the VOC 2007 dataset. So you can see that basically the YOLO 1 is much faster than the Rcnns, right? Here we have Rcnn, which is the most basic one. So let me make this one, right? Here we have Rcnn, which is the most basic one. Fast Rcnn is a little bit better. So this is a mean average precision is basically a measure of accuracy, and frames per second is a measure of speed. So obviously the best models are around here. So faster Rcnn, faster Rcnn ResNet are all they tend to be higher accuracy than these models, for example, at least than YOLO, but they're much slower. And here we have SSD 512. There is I believe this to be 512 layers, and then here SSD 300, and then you can see that how this is compared with the YOLO. So now, today we have many different versions of YOLO and SSD. I think the latest version of YOLO is, if I'm not mistaken, YOLO v5. And this was taken from YOLO v2. So actually, it would be interesting to look at what are the performances of the newest models with regards to this. But the point is that these models, yes, either YOLO or SSD, they are generally faster than the Rcnn uh, methods for detecting objects. That is because they are unified, right? Whether which one is more accurate than the another is debatable, and it depends on the architecture that you have. But definitely, SSD and YOLO are state of the art because they are faster than the other ones. Okay, so we are gonna go take a look at the first code for today, which is face detection. Before that, we're gonna take a 5 minutes break, but you guys are welcome to find the code and the model by following this URL. Maybe can we post the URL in the chat? Yeah. So please, in these 5 minutes, try to find some time to to download the code and the model because you're gonna need it for the next part. Okay, be back in 5 minutes. Okay, welcome back, everybody. I hope that you had a nice 5 minutes break. So if you haven't managed to go to this URL, I'm gonna demonstrate just that you can go here, right? This is the big bucket page for our code, and here you will see this model. So this face detection retail 004 is the model that we'll be using today. These are just the diagrams for the code, the ones that are in PDF version. And then here we have the code for face detection, which is the one that we're going to be working today, right now. And also face social distances, which is going to be the second code for today. Okay, so let's start coding. I'm going to pull out my editor, as well as the pictures. So, excuse me. Okay, so as I am coding, I think my assistant Jacob will be explaining the diagram.
Okay, so the figure is the host device diagram of the face detection using the SSD model. And let's see the device side first. And the color camera, which is the middle camera or in the optic, and will giving the control input. And the color camera will output the RGB frame. Then this RGB frame will be sent to the host side by the SD download. Also, it will be sent to the function called image manipulation, and it is just a function to resize the image frame from the 500 times 500 to 300 times 300, which is the request input size of the SSD model. So after we get the prediction results from the model, and the face location information will be sent to the host site by the SD node. So now we already have the image and the location information in the host site. And we can use in the box to visualization the face location. So that's all. Thank you.
All right, thank you, Jacob. So let's start coding this. So from the diagram, we can see that we have 3 different nodes here. The first node is a color camera, so that's what I'm creating right now. Since I'm gonna use that model, that is the one that you saw in on the big bucket, I need to set my OpenVINO version to this version. That's just needed so that we can run that model. So another thing is that we need to change. So we need to define our color camera object. So it's going to be pipeline create color camera. Okay, and then I'm going to need to set the preview size. So what size am I going to reset it to? Actually, because the predictions of this neural network come in as fuzzy values, so they come, for example, they give you the location of the bounding box in between 0 and 1. So we want to bring it back to the original image. So I'm gonna just set it to some parameters called preview W, preview height, and this is gonna be also parameters that I'm going to give as input to my function to create a pipeline. And then I'm going to define that outside. So I'm gonna define it so that it can be 500 times 500. So it's gonna be frame size 0 for preview W, frame size 1. Okay, so as I always like to say, we need to be testing the code as we go through. Created color camera object. So let's run this code to see if we actually get something that is working. Okay, no problem. We created it and it's no problem. The next thing will be to create this image manipulation node. So we call it just manip. It's going to be die create. So there's actually not a fast way to create this image manipulation node, but you can just go die create die node and then image manipulation. And then you want to set. So what this manipulation does is that it's just going to resize the image to the size to another size. And now explain why. We're going to resize it to 300 times 300. That's because this model is specific, requires that the input image is 300 times 300. But if I just pulled out that image and display it, it will be very small for us to see. So I'd rather have a different size of the frame for displaying, right? So I have my manip size. I need to set it like this. And it resize as 300 times 300. I think that's the only thing. Create image manipulation node. Okay. So I'm gonna run this. Oh, okay. Detector has no model create. Oh, it should be pipeline. Sorry. Pipeline create. Let's see. Okay, no problem. What else do I need? Okay, I need my RGB, my face detection model. So then I'm gonna go that my neural network is gonna be my pipeline. Create. In this case, it's a mobile net detection network. And then I'm going to set block path because the model wants to know which model do you want to use, right? This thing wants to know the path. So in this case, I have my code here. So I have this is my script that I'm working on right now, and my model is just right outside. So I'm just gonna come here, rename, gonna copy the name of that model, and then just gonna print it outside. And don't forget that I need to make it .blob. So I'm also gonna give this as a parameter, as an argument for my function here. Okay, so now it should be fine. Let's see if this can run. Yes, I think it can run. What other thing does it want? It wants to know to a confidence threshold so that it can know which detections to pass and which detections not to pass. So we usually set this detection to 0.5. Face detection. Okay, so just one thing that I would like to make clear, that this is a face detection neural network because this model has been trained to detect faces, right? If this model was trained to detect cars, it will be a car detection neural network, right? So in this case, it's a face detection neural network because it has this model. What else do we need? Oh, one very important thing. RGB needs to set interleaved as false. Could Rick explain to the audience why do we need to set this value as false?
Okay, so the RGB image for data, they have two options. One is the internal leaf, and number two is the planar. So the difference between them is the planar is like the usual RGB frame, like have three channels, one for R, one for G, and one for B. If you use the internal leaf, your internal leaf means that now your image frame will become the just one channel. Like you have one pixel is represent R, and next to the pixel is the same pixel but the ray number, and the next will be the green. So instead of a three channel, you will actually become the R, the next is the G, and next is the B, and next is the next pixel of R, and next G and next B. Yeah. So that's the difference. And the model require the planar. So in here we say the internal leaf as a false.
Yes, thank you, Rick. So if we didn't set interleave to false, the model is not going to receive the shape that it wants, because it wants that specific shape so that it can do the predictions, right? So let's move into the linking. So what am I linking? Linking what with what? The color camera needs to be linked to this X-link out node so that we can get the original frame. Then its preview also needs to be linked to this input manipulation node. Then the next thing that I need to get is from the manip out, I need to link that to what? To the RGB frame to the face detection model. Gonna be linked to the neural network input. And lastly, I need to create an X-link out node for my detections, and I need to set a stream name. Let's call it yeah, X out, and then or whatever. Okay, so then the last thing I need to link is my nn.out link to my X out nn.input. Okay, this should be fine. So when I print finished creating pipeline. Okay, let's run this code to see if everything is running correctly. Boom, 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 boom. 4 things that it printed, so that means that there's no problem. Perfect. So now I want to give you a reminder of what is the things that we're doing. We import the required packages. We define our pipeline, right? Now the next thing is to start our pipeline. So then pipeline is device equals device into which pipeline, but the pipeline that we just created, and then device start pipeline. For those of you who have an OB at home, once I run this code, remember that once I start my pipeline, I should hear the camera make a noise, like similar to what you would hear if you plug a USB. Okay, did it. There's no problem. Okay, so now we need to define the queues. So we have queue RGB, this device, get output queue from where? From the one that I named RGB, because this is queue RGB. We have a max size of 4 and a blocking behavior of false. Then we also have queue detections. It's gonna be device get output queue from which queue? From the one that is called X out and N. Okay, so that's gonna be the queue that contains my detection. So now we're gonna move into the post-processing part of our algorithm. So the first thing that we need to do is that we need to get the stuff from the queue. So in RGB is going to be queue RGB get, and then in detections is going to be queue detections. So there's where we come to a tricky part. Not all the time you're going to get a detection from this neural network, because there could be stuff that there could be times that a face is not visible, right? Or maybe it's not visible as the model would like it, so it would not give you a detection. So in this case, we need to do try get. We do this because we want to avoid possible bugs that could come. And this method is better for checking if there's a detection or not. Okay. Next thing will be we need to get this RGB frame by saying RGB frame is in RGB get CV frame. Remember, we always do this part because otherwise it will be in a different format in a depth AI image array, so that's not easy to work with. So now we have this. So now we need to check the first step. So what do we want to do here? We just want to get the detections and just plot them in the face, right? So, but the first thing that we need to do is we need to get the detection. Okay, so the first thing is if in detections is not none, that means that there is something there, then my detections is going to be in detections, and then which part? This contains different parts, but I'm just gonna get the detections part. Okay, and I'm gonna save it to I'm show my RGB frame, and I'm gonna show my RGB frame, and then if remember to write that condition to terminate if CV2 if CV2 wait key 1 is equal to ordinator key Q, then what? Then I'm gonna break the loop. Okay. So so I have my detections, and now I want to plot each detection because I could have more than one detection. I could have, for example, 2 faces on the screen, right? So for detection, detection in detections, what am I gonna do? Well, I'm gonna define a bounding box. My bounding box is going to be the first item in my bounding box is gonna be detection x. Let's have x mean, y mean, x max, y max. But remember that this come from impulsive values, so I give you from 0 to 1, right? They're normalized, so we need to go bring it back to real pixel values of the image. So we multiply times frame size 1 because 1 is related with the x. Then the next item, and we make it integer, so because OpenCV likes integer values. So the next one is detection. What part of the detection? Y mean. And then we times frame size, and then we multiply the second element. Okay. Then we go x max. Detection x max times frames times frame size 0. And then lastly, it's gonna be integer of detection. What part? Y max. Oh, times frame size, the second one. Okay, then let me make this all a tuple so that I can put in my bounding box. And then what am I gonna do next? Well, the next part would just be to plot a rectangle, right, on the bounding box, and a rectangle on those detections. So let me do CV2 rectangle. Okay, the first parameter here is where am I gonna plot this rectangle? That's gonna be in my RGB frame. The next thing is we want 2 tuples. The first one for being the the 2 points where you're gonna draw your box. So here is x mean, y mean. So this is b box 1. Then is b box. I mean, this is the first element. This is the second element. Then is b box 2, and finally b box 3 for the fourth element. What is the next thing that it wants? If I'm not mistaken, I think it wants the color, so let's plot a blue. So, and then the last thing would be the line width. So what happens if I run this? Aha. Okay. So here, so the students in the lab, my lab mates, they have decided to just print many different copies of my face and place them everywhere. So this is just a picture of me. See, and you can see uh, how it is detecting our faces, right? So we have successfully created a pipeline that, okay, let me stop this. But we have successfully created a pipeline that can use the OGD to collect RGB data and use this RGB data to pass it through this neural network, this object detection network, SSD network, and we're able to extract the predictions of the locations of the faces and plug them into this image. So this is the first code for today. We're going to take another 5 minutes break. And on the second part, we're going to build upon this code, right? We're going to extend this detection into 3D by using spatial AI. And you will see how it's super, super, super easy to do it. In this case, we have less than 60 lines of code, and we're able to draw, to define this pipeline and to have something that is working. For the other one, it's also super, super easy. And then we're just going to create a system where if two people are close to each other, then it's gonna do something, right? It could, well, then you will see later. And let's take a 5 minutes break here, and we will see you very soon. Okay, welcome back, everybody. So we have just taken that 5 minute break, and now we're gonna move into the second part of our code. So here we have the second diagram. Oh, this is too small. How about? See better? Yes. So for this part, I think maybe my assistant Rick can explain what is it and how does it differ from the previous part.
Okay. So in this code, we will use the same model as last previous code. But in this example, we want the 3D information, right? So we will use instead of the regular neural network node, we will use a node called spatial neural network. So let's see how it works. So inside the pipeline, we will create the color camera, which will provide our preview. And this camera will also send the preview to another node called the manipulation. And this code, we just use this code for resize the image to fit to the model. And beside the color camera, we have the two mono camera will also link to the stereo depth. And the stereo depth will provide our depth information. And this depth information will link to the spatial neural network node as the input depth. And the image being resized by the manipulation node will link to the spatial neural network node as the preview link. So what we will get from this node, the spatial neural network node. So the spatial neural network will provide us the location of the bounding box, and also they will provide a x, z, and y coordinate information. So in the whole site, we just need to get these detections and combine to the RGB frame and draw these lines, rectangles, and show the numbers. And if you remember in week 2, we also do the same thing. We also get information from the map, but that time we use the map and get a pixel of a corresponding region of interest in the whole site. This means we get information about our ourselves. But actually, we can do it like use the node that I provide, and it will be super easy, and also there will be few line, easy to use. And I think this is one good thing that we use the API. So this is my explanation for this figure.
Yeah, thank you, Rick. I think it was a very good explanation. So while you were talking, I was creating the nodes that we see on the diagram. So basically, I created these monocamera objects, right? And I assigned each of them their respective board sockets. And I also defined this stereo object. So this stereo is just gonna take the input of these two, and then it's gonna output the depth map. And then now I'm just linking everything together. I'm gonna link these two to the stereo, as you can see. Here I'm linking these two to the stereo left and right respectively. Then I'm also going to link the stereo depth, the depth part, to the neural network, which I also change here. And I assign these two, uh, these, oh, these other two parameters, which is the upper and lower threshold for the depth. So this just so that I can better analyze depth within this range. Then I'm gonna give it to the then I'm gonna link this one to the input depth part. Oh no, input depth part of the neural network. Okay, let's see if it is running or it's gonna give me an error. Okay, so you see it's still running because the spatial detector neural network still gives me uh the position of the faces, but I can also extract more information, right? So the first thing that I want to do is I want to print the spatial locations of my face. So how am I going to do that? So the first thing is I'm gonna put text. So I'm gonna see to put text. Where am I going to put the text? In the RGB frame. And the next thing is what text do I want to put? Well, that one is going to be spatial detection. Now the detections can now these detections will contain another let's say object is called spatial coordinates, and this thing contains this spatial coordinates object contains three different objects. We're going to take the X one first, and this is going to give you the position of the object that you are describing that we have. So in this case is the face in terms of millimeters. So I want centimeters, so I'm going to divide with that remainder for 10. And then for all of you who are engineers, you need to remember to always include the units. Then the next thing it wants is the where do you want to put this one. So I'm gonna, it requires a tuple. So I want to put it on my face, right? So I want to, but I don't want to put it exactly on the corner. I want to put it a little bit down. So I'm gonna add just 30 pixels to that. The next thing that it wants is the font Hershey triplex 2. And then if I'm not mistaken, it wants the line width and then the color. So let me plot this one blue as well. Okay, let's see what's up when I run this code. Okay, so now it is telling me, oh, why is it so big? Maybe we should make it a little bit smaller. It looks a little bit ugly. So now it's telling, okay, let me make it a little bit smaller because it actually looks not so good. Okay, so now if I move my face is slightly to the left, right, in this slide. So if I move it more, okay, more to the left, you can see how that value that is being printed increases. And if I move it to the center, it goes to 0 because it's a relative position relative to the camera, right? Then if I move it to the other side, you can see how that value increases. So the camera thinks that there's roughly what 25 or something centimeters on both sides, which seems accurate because the camera is also like a perpendicular to my face. If I, for example, instead of having this, I have the camera like this, and I move my face like this, it means that there's a 27 still. Okay, maybe this is not the best position. Maybe like this will be the best position. If I, so it thinks that there is a, okay, so I cannot get this slanted. Okay, it will be like something like 27, but only 10 here because the camera is a little bit slanted, right? So let me put it back perpendicular or as much as you can. Okay, those 25 centimeters seems like a good estimate because this ruler is roughly 50 centimeters. Okay, let me run the code so that I can. This ruler up until here is 50 centimeters. Okay, maybe that's not the best ratio. Let me continue doing this for the X and for the Y and the Z. I think for the Z one is much more easier to see what it is doing. So let me continue to do that by saying detection spatial coordinates Y divided by 10 plus the unit, which is centimeters, and then we have where we want to put it, B box 0 and B box 1, and I want to move it a little bit down. So let me move it 50. Then CV2 font Hershey triplex 0.5 and also make it blue. And then let me continue to do the same thing for the Z direction. Then we have the Z and we make it a centimeters. And we always add the unit. And then where we want to put it. So B box 0 and then B box 1, but we're going to move it 70 pixels down. Then the font size, font Hershey triplex, line with a 0.5 and blue. Okay, I think this will be much more easier to see. In here, we want you to see what it's doing. Okay, something is not an umpire array. Oh yeah, some parentheses issue here. Oh, because it should be a comma here, not a dot. Okay, so this is telling me that there's roughly a meter between me and the camera. I think that's an accurate estimate. Oh, in the camera. If I, for example, put this thing, this ruler is roughly 65. And what value am I getting right now? 70 something, right? That is because how does the depth AI come up with the values to put in here, right? So that's basically the average of all the pixels that are inside this bounding box. But you can see here, my face contains also pixels from the background over here and over here, right? and even for my neck is a little bit farther away here as well. So that's why OpenCV tends to give me like a little bit detections that are a little bit like overestimates of the depth, because that the bounding box is encapsulating the stuff from behind as well, right? For example, so on the for the X one we already see, right? And for the X we need to notice that it is the center of the bounding box, right? Because it's the average. So for the Y, the same thing, right? If I go above, let's say a middle line here of the image, it gives me positive values. If I go below that image, it gives me negative values, right? So you can see how it does it for this one as well. For the X and for the Y, so positive, negative. Okay. So now the next step that we want to do is we want to compare the detections, and we want to look at, now we know the position in the 3D space, right? So now we want to compare these positions, and if if the distance is smaller than something, let's say half a meter, then we will do something, right? So for that, we need to iterate through the detections. So let me do that by doing like this. So for I and detection in enumerate detection. So that's gonna be my first loop in my nested loop. And I'm going to compare each one with all the other ones. So for J and detection 2 in enumerate, what am I going to iterate through? The same sections. And then if I'm going to compare these two, I'm going to get a matrix that is symmetrical. Maybe can one of my hackers tell me what is a symmetrical matrix?
So symmetrical matrix basically is because our matrix will have the row and the column. So it's the row. Simply say is the row position I will be same as the value will be same as the current position I, and so this I can be the 1, 2, 3, 4, 5 to n, and so this is how I'm thinking. Thank you.
A symmetrical matrix is a matrix that if you look at the diagonal and you fold it, right, then the overlapping elements will be the same. In other words, I comma j of if I have a matrix A and then I look at I comma j, that item is going to be the same as the j comma I element in the same matrix A. So that means that I I I will do the double computation, right, if I look through all of them. So what I'm going to do is I'm only going to take the lower triangular. I'm only going to calculate the distance if these are in the lower triangular, right? So to avoid double computation. And I'm not going to calculate the distance of an item in itself because that will be 0. So that's why I just determine that I'm going to get the lower triangular by just saying if I is less than j, then I'm going to calculate the distance. Now, as we saw on workshop 2, where we calculate the distance of the 3D of the points in the 3D space, the distance is quite a long formula. So we are going to just define a function to do that for us. So we're gonna have the dx, which is the difference in x, is gonna be, and I'm gonna assume that I have this point 1 and point 2 that which are a tuple, a triplet that contains the position of the points in the 3D space. So x, y, z positions of the points. Of dx, it's just simply gonna be point 1, the first element. Oh my god, why is doing this? And then point 2, the first element also. The y is gonna be point 1, the second one is point 2, the second one. DZ is going to be similar to what we have before, 0.1, except that it's not going to be the third one, 0.2. Oh my god, no. And it's going to be the third one as well. And we're just going to return the square root of dx squared plus dy squared plus dz.
At the line 62, you type wrong.
Oh yeah, dz. Yeah, my bad. Thank you. This should be dz. And then we want to return a rounded value because otherwise the number will be super large. We don't want that. So we want to round to the first decimal points. Thing looks fine. Okay, so then this is going to require the distance of, so okay, let me define my 0.1 is going to be my detection spatial coordinate x divided by 10. Then it's going to be detection spatial coordinates y divided by 10 to get in centimeters. So everything needs to be in centimeters. And then detection spatial coordinates z divided by 10. We need to make sure that we have a tuple for this thing, otherwise it's gonna not like it. Then for 0.2, so 0.2 is the one from my detection 2, right? So it's gonna be detection 2 spatial coordinates x, same thing, detection 2 spatial coordinates y divided by 10, and then detection 2 spatial coordinates z divided by 10. We want to make this a tuple. And then distance is simply calculate distance of 0.1 and 0.2. Okay, so now I want to append my results into some different array. Let's call my array distance results. And I'm going to append some kind of dictionary. Okay, so first of all, I cannot append stuff to an empty array, so I need to create my array here outside. Distance result is going to be an empty array, initialize as an empty array. Okay, so the first thing that I'm going to append is what? The distance. So I'm going to append the dist. It's going to be the distance. The second thing that I'm going to append is a Boolean variable telling me, are these 2 points closer than a half a meter or not? Then we call that dangerous. And then, so for a Boolean, I just need to give it a if condition. So if the distance is less than should be 50 centimeters, so that's half a meter. Yes. And then I'm going to append detection 1. So I'm going to append the detections. Okay. And okay, let me see if it's running. We won't see anything change, but okay, there's no problem. So now I want to iterate through my list that I have. So for result in distance results, I'm going to, what am I going to do here? Okay, first thing I want to do is, as you can see here, I want to make a line between both of my detections or all the detections. So the first thing would be to do CV line. But that line needs to be from the middle of the bounding box to the middle of the other bounding box. But I don't want it to cover my face, so I'm going to move that line maybe to this point here. So let me do that by say x1 is going to be the mean of what two things? The mean of result detection 1, the x mean, right? And result the same detection 1, the x max. So that's gonna give values in 0 and 1. I still need to multiply this and to scale it to the frame size times frame size 0, and I need to make all of this an integer because I want to plot that. So when I want to plot, OpenCV likes integers. So then for y1 is simply the integer of result detection 1 y max, and that should be scale times frame size 1. And for x2 y2 we're going to do the same thing. Going to be the int of the empty mean of what? Well, result detection 2 x mean result detection 2 x max, and all of this times frame size 0, and y2 is going to be int of result. Instead of detection 1 we have detection 2 and the y max. I'm going to scale this times the frame size 1. Okay. So I also want my, in addition to this, I want my, so what am I going to do, right? So if the distance between these two things is less than 0.5, I want to make this line red. Otherwise, the line will be blue. So you could have many different conditions that happen when distance is less than a certain value. For example, you can sound an alarm, you can call the police, you can spray water on the people or whatever, or display a sign. In this case, we're just gonna demonstrate what can happen if just by changing the color of the line. So let me define this color variable that is going to be red, VGR. If my result shows it is dangerous. Else it's gonna be blue. Okay, so let me make the line. So I'm going to CV2 line from, well, where do I want to plot this? On RGB frame. So this is the first point, second point. So the first point is simply x1, y1. The next point is x2, y2. And here is, I believe, is the color, if I'm not mistaken, and then the line width. Let's see what does it give me. Okay, so in this case, it is plotting the line exactly where I want it, which is in the middle of this part. And then it's plotting it red because it's telling me that these two things are less than half a meter. Okay, so in distance. But I still want to know, for development purposes, I want to know what is the distance between these two things, right? So then for that, I simply just uh, tell it to plot the distance form to put the text there. But I want the text to be put on the middle of the line. So I'm gonna go x, gonna create a new variable. X dist is going to be just simply the mean of x1, x2. And remember that we want integers for this thing. And then y dist for a distance is going to be the integer of the average of the two y's. Okay, why there is a... Oh, because I have an extra white space here. Okay, so then the last thing that I'm gonna do is just to put text. On where? On the RGB frame. What text am I gonna put? Well, there's gonna be result distance, right? And then don't forget to add your unit. And then the next thing will be, where do you want to put it? Well, we already calculated those 2 points, x dist, y dist. And the next thing will be the font. So CV2 font Hershey triplex. Then it will be the line width. And lastly will be the color. That would also depend on whether the two things are close or not. So let's check what are we getting when we run this code. Okay, so there's my face. There's the other face. And you can see that when the two are close, it is red, less than 50 centimeters, right? Half a meter. The two things are far away, it is blue. Meaning that our social distance system is working properly, is working well. Close, red, far away, blue. What if I change positions with this thing? So now my face is here, and this thing is here. Red, blue, red, blue. I mean red, and then blue. So with that, we would like to finish our hackathon session for today. I would like to thank all of you for supporting our lab. Please give us a like if you like what we're doing. For next time, we will do some more interesting stuff like this, but with post estimation. So we will be waiting for you over there next week, the same time. And thank you all for showing up, and we appreciate you all. I also would like to thank my team and everybody involved. There's a lot of people who are working here. So yeah, please give us support us by giving us a like. We will really all appreciate that. So thank you.